Okay, so here's the solution to test number 1. So the first problem is worth 10 points, so each one is worth 2 points. First problem, it's multiplication, so you take the term with the least number of significant figures, and that determines the significant figures of the answer. So we have 3 here, and we have 4 there, so the answer is going to be 3 significant figures, 57.0. The second problem also is multiplication. We again have 3 significant figures. 3 here, this 0 is significant, so is this one. So when you multiply them together, you get 4.20. Here we have 2 significant figures and 4 significant figures. So for multiplication and division, you take the term with the least number of significant figures, which in this case is 2. So the answer is 2. The fifth one, we look at the digit that has the least accuracy. So here to the tenths, that's thousandths, tenths. So we need an answer to the tenths. So we add these all together and we round off to the tenths place. We get 49.2. Here, this one is only 2 significant figures, and it's to the tens place. So when you add all these things up together, you get something like 207. But the 7 is not significant because this 0 in the first term makes it such. So we have to round up to not 2 significant figures, but to the tens place. Okay, next problem. You had a car traveling at 63 miles per hour for 15 minutes. So you have to convert minutes to hours. So you just divide by 60. So this is 0.25 hours times 63 miles per hour. You get 15.8 miles. Now, I've got 3 significant figures here, but I'm going to round off at some point, which I don't think I did actually. So let me fix that. So this should be 31. So we do the same thing for the second period of time, 32 miles per hour for 28 minutes, which is 28 divided by 60 for hours. You get 14.9. You add those together, you get 30.7. But because these are all 2 significant figures, we are going to, and especially to the ones place, we're going to round it off to 31 miles. Now the total time is 15 plus 28 minutes divided by 60 to give you 0.717 hours. So to get the average velocity, you take the distance traveled divided by the time. Now I brought one of those significant figures back into play here to do this calculation, but then I rounded off. Now if you take the average of these 2 speeds, 63 and 32, you'll get 48, that's wrong. That's the average of the speeds. This is the average speed or the average velocity. Okay. Next one here. Now I didn't show a sketch, but I'm just showing you the method. So you got an initial velocity, 12 meters per second. It's slowing down, so it's going to be negative acceleration. And it's 1.2 times 10 to the second. The reason I did that was because I wanted to show that it was 2 significant figures instead of 120, which would still be 2 significant figures. But so I've converted 1.2 times 10 to the second into 120 meters. So these are the 3 things I know. And so I can use equation number 4 because the thing I'm solving for is the final velocity. So you can just plug the numbers in with the units, and if you solve for v, you'll get 4.4 meters per second. So that's positive. And remember in class, I double-checked to make sure that I did the problem right, because what I did was I set v equal to 0 and found out how far it went. It was more than 120 meters, so I knew that this would actually work out. And then to find the time, use the second equation, solve algebraically for the time. And a lot of you guys didn't solve algebraically for the time. Still encouraging you to do that. Okay, so V is positive 4.4. You subtract 12. V0 is positive, so you subtract positive 12. Divide by the acceleration, and you get 14.6 seconds, which rounded off to two significant figures is 15 seconds. Okay, the fourth problem. So we have this person that throws the ball straight up in the air. It goes past this balcony. It's still moving at 3 meters per second. Because of that, it'll still go up for a little bit further, and then it will loop back. Well, it won't loop, but it'll go back on the path that it's already been because it's one-dimensional motion, and it'll reach the same level here. So it's going up 3 meters per second. The question is, what was the initial velocity to go through this vertical distance and have 3 meters per second here? Given that the initial velocity here is 3 meters per second, how much further does it go until the velocity is 0? And then the third question is, when it comes back down to the same height as this condition, what is the velocity? So the first part is calculating the initial velocity. So these are the things we know. We know the final velocity here is 3 meters per second. We know that the acceleration is negative 9.81 meters per second squared, and we know delta y is positive because we're going positive y direction upward, as it says right there. So delta y is positive. Acceleration is negative because force is pulling it towards, gravitational force is pulling it down instead of up. So again, we use this equation to find the initial velocity. So here's the equation, and if you solve for the initial velocity, you'll get initial velocity squared is this minus that. You plug in your numbers and you take the square root, and again, because you're throwing it up, we know that we take the positive square root. And if you look at the number of significant figures, you can see everything is given to 3 significant figures, so the answer should be 3 significant figures. So that's my initial velocity, which I didn't try here. Okay. The second part is just when it goes past the balcony. So my initial velocity there is 3 meters per second. The peak is 0 meters per second, and we're still under the same acceleration conditions. So equation 4 again, in this case, v2, or the final velocity, is 0, so we can set that equal to 0. And if you algebraically solve for delta y, you'll get delta y is negative v0 squared over 2a. v0 is positive 3 meters per second. A is negative 9.81 meters per second squared. So you find out that the additional height is only 4.6 meters above the balcony. Now, in this problem and the next problem, anytime you, and I've said this many times, anytime you try to take the square root of a negative number, you've done something wrong. Go figure it out. Okay, so there's 2 errors there. One is you've done a math error, and the second one is you haven't recognized when you've made a mistake. So I don't know if I might take off for both of those. You might think it's the same error, but one is maybe using the wrong numbers to start with, or doing an algebra error. Then there's the error of not figuring out you made a mistake. So the other one is if you ever get negative time, then you've done something wrong. You need to go figure out what error you made. Now, the third part, you actually don't have to do any calculation. Because of symmetry, it's going up at 3 meters per second here, and when it comes back down, it's going to be going down at 3 meters per second. So it's negative 3 meters per second. Now, some of you went through the calculation with v0 equals 0 and acceleration equal to negative 9.8 meters per second, and delta y equal to negative 0.46 meters per second, and you'll get the same answer. But you didn't actually need to do the calculation because it's for symmetry. Pretty much everybody got these right. There are a few people that put an extra significant figure on here, but this is not significant. Oh, now my screen's being weird again. I don't know what caused. I had to reboot my computer last time. Okay, we'll limp through the rest of this. Likewise here, this is a significant figure. So here it's not a significant figure. Here it is a significant figure. Because this one is just a place setting. If I didn't put the 0 here, it would be 13. So this 0 needs to be here. If I put a decimal point, then yeah, it would have 3 significant figures. Here, this 0 doesn't need to be here. It's telling us something. It's telling us that there's an additional significant figure. Okay, then the final problem. So this balloon is going up, and the sandbag is going up at the same speed. So the initial velocity of the sandbag is positive 2.75 meters per second. Acceleration is negative 9.81 meters per second squared. And delta y, which is the distance from where the bag is dropped or let go until it hits the ground, is negative 25 meters per second. Again, we're defining positive y going up. So the first part of the problem has the bag going up and all the way back down again. So we don't have to calculate intermediate conditions. The final condition is when delta y equals negative 25 meters per second. So again, we can use equation 4 with this being v0 because the balloon's moving up. Delta y is negative. And I realized I wrote 25 here, but I used 23. So this is 23. I told you to ignore the numbers on the picture. I think everybody did. Okay, so if you use 23 and you solve for v, you'll get plus or minus 21.4. But because the bag is falling, you choose the negative solution. And there's 3 significant figures. Now, once you have the velocity, then you can calculate the time. So you take equation 2 and solve for t. So the final velocity is negative 21.4. You subtract the initial velocity, which is positive 2.75. You divide by negative 9.81. Again, if you got a negative time here, don't just ignore it. Go back and figure out where you went wrong. So when you solve for this, you'll get positive 2.46 seconds. So that's how much time it takes to go up to its peak and then fall down and hit the ground, or just before it hits the ground. And then the final question is how high above the ground does it go? A lot of people said 25, but remember it goes up a little bit because it has some initial velocity because of the velocity of the balloon. So our initial velocity is 2.75 meters per second. Our final velocity is 0 because we're at the peak. Acceleration is negative 9.81 meters per second squared. And if you take equation 4 again and solve for delta y, you'll get v squared minus v0 squared over 2a, with v being 0. So you get negative v0 squared over 2a. Again, delta y has to be positive because it's going up. And you add that to the original height that it was let go at, which was 23 meters. And I should have rounded that off to 23.4 as the answer. Okay, so that is the first test solution.